Hello, everybody. As always, if you're watching live with us, please feel free to ask any questions along the way. If you think you might like to come on the show yourself, please do get in contact. My details on the channel's About page. Next week, we'll be talking with Sam Underwood, who's does all sorts of work with experimental musical instruments. But today's guest is Joey Castillo. Hello, Joey.
Howdy.
Would you like to introduce yourself quickly?
I'm Joey Castillo. I'm a purveyor of oddly specific objects, I suppose.
I love that name, I have to admit. The first time I saw it, I was just like, that is so good.
Thank you.
So as is typical, I like to start sort of at the beginning of everyone's life, where they were when they started out and how they got to where they are today. You mentioned that you started out in film school and journalism. Can you just talk to us a bit about that quickly?
Yeah, for sure. I mean, I don't know. I don't even know where I decided to go to film school or journalism school. I don't know where to get started to go to journalism school. Actually, I was in film school as an undergrad, and kind of realized that I was 20 years old and had nothing interesting to say, and I was out there with this newspaper, realizing people have stories, and like I want to learn their stories, and so I went to journalism school. From there, it was like the 2010s era. Newsrooms were kind of pivoting to multimedia, and I thought, oh yeah, software and storytelling. I can use some of my tech, like I did some like comp sci stuff in high school, so I'm like, I'll use my tech background to like do software and storytelling. Kind of fell into lifestyle journalism, doing cocktail apps for Food and Wine magazine, and then just kind of decided to go into making the technology.
Very cool. So I think at one point you got involved in an interactive film as well. Is that something you can talk about a bit here?
Yeah. So a couple of years back, I started working for this company called Mindsight, or now Podop. They did an interactive Steven Soderbergh film called Mosaic, and it was really cool, actually. I was doing iOS apps at the time, which I guess I kind of still am in the iOS world. But yeah, it was very interesting. It was kind of imagine like a fixed story world where characters kind of come together in various ways. Like, there's like right now, for example, like you and I are having this interview, and at the end of it, you could choose, do you want to follow Joey? Do you want to follow Addie? Right. And at the end of that, you might follow me around for a while. And then when our lives intersect again, you'd have details of my life, but not your life. And so it was a murder mystery called Mosaic. And depending on which pieces of the path you followed, you might have different ideas of what really went down.
Right.
So yeah, that was the interactive film thing, and I really enjoyed it. It was a fascinating thing to work on.
And so how did that work from a technological point of view? Was that very sort of play a clip, offer a couple of choices to the viewer, and move on to the next step, or how did that go?
To a certain extent, yeah. And it was like, streaming and preload, and there were some VFX things happening to like composite these like little cards into the screen. Looked kind of a lot like this, like two different directions to take, these like split view kind of things. But so that was that. And actually then Bandersnatch came about a few years later, and anyway, yeah, it was interactive filming at a moment, but it seems like it's a little bit fallen off at this point.
Right. Fair enough. Yeah. Very good. And so, you're talking about your life as it stands at the moment. You're doing 6 months of sort of consulting, contracting type work, and then 6 months of working on your gadgets. That's fantastic.
That is the ideal. Yeah.
Fantastic. Well done for arranging that. Can you talk to us a bit more about what you do sort of in the software world?
I mean, I do like iOS stuff. I mean, I'm right now working on a Django app, which I hadn't touched Django in a while, but I guess I reluctantly have to call myself a full stack developer now. But yeah, just iOS stuff. I mean, for clients, just that sort of thing.
Yeah, fair enough. Okay.
Usually these things are kind of project oriented, where someone wants something made, and it's like you can roll onto the project, you can hand off the project, and,
Yeah, nice. Okay. And then the big topic for today would be your 6 months a year of gadgets.
I guess that's the topic.
Yeah, so we've got loads of exciting things to talk about. We've skimmed over your past very quickly because we've got so much lined up. Let's start with your LCD Featherwing and have a bit of a chat about that.
Sure. Yeah. So I guess that is this little guy.
There you go.
So yeah, I mean, it starts with the sensor watch, which some people might be familiar with, but if not, it's just a Casio wristwatch. I took it off. I was wearing it until earlier.
So the Featherwing was actually after the sensor watch, was it? Or I presumed it was actually before, to sort of prove out the LCD stuff.
No, it was after. I mean, I got into the sensor watch thing, and after like a year of working on it, I realized I know a little bit about LCD displays. I know a little bit about LCD technology. So why not like take that and go back to my roots, which is like I cut my teeth on Feather. My first project was called the hiking log, and it was a GPS Featherwing on top of a feather that would log my temperature and location on hikes. So
Okay.
like I'm always reaching for Feather in my experience and like random projects. So I'm like, why not build a Featherwing that uses LCD technology? No one's done this yet. You know, Adafruit has TFT displays. They have OLED displays, which are all great. But an OLED's going to use between like, you know, 8 to 20, 25 microamps,
Yep.
milliamps,
Yeah.
depending on how many pixels are on. A TFT obviously has that backlight because you got to shine through the layers of color filters. But an LCD is kind of great because it just has this reflective sort of affect to it. So
Yep.
there's no light coming from behind. You're just ambiently reflecting from the background what light is around and blocking it selectively. So this display ends up using something on the order of 12 to 15 microamps of power, which is
Amazing difference.
0.0125
Yeah.
milliamps. Did I make that right? No, 0.00. Yeah, 0.0125. So anyway, the point is, it would be a really great low power display technology. And actually, I'm going to pull this one out. So this was a little one that I made. It's just a kind of stacked feather. You've probably seen this before. And with this 400 milliampere hour battery, so it's always on display, uploading data to the internet every 15 minutes. This gets between 14 and 16 days of battery life on a charge, which for something this compact is not bad at all. And
Yeah.
if you wanted to, you know, double the battery size to 800 milliamp hours, then you could expect to get a month of battery life. So
Okay.
yeah, it's just a really great low power display. And again, like the display is always on, and you only really consume more power when you decide to update it.
That's very cool. So, what went into designing the LCD? Because that's something that I think, well, me in particular, and I'm sure a lot of other people have just no idea how you'd even go about starting that.
Yeah, totally. Well, I mean, I can actually pull up the, you can throw up my other screen.
Yeah, sure. Let me do that quickly. There we go.
Yeah, so this is actually the data sheet that my manufacturer sent back to me, but this graphic itself was actually designed. I designed it in Affinity Designer, which is a
Okay.
piece of design software, not unlike Adobe Illustrator or something like that.
Mhm.
And yeah, so like number one, you design vector artwork. The one thing you got to understand is, oops, Affinity. No, I didn't want you to come up quite yet. So the way that these things work, you can energize an individual segment by energizing a common segment pin. We can go into the details of how that works, but the gist of it is you have to be able to address each individual segment. So in this case, I have 16 pins. There's 4 common pins and 12 segment pins. You multiply that out, that means you have 48 addressable segments. So
Right.
you have to come up with a design that has no more than 48 individual things you want to address.
Mhm.
So, for example, each of these individual 7 segments of this number 8 here are individually addressable because I want to be able to display any number from 0 to 8 or
Yeah.
certain letters, right? But this Wi-Fi indicator, which has 1, 2, 3, 4 segments, I can't address those individually because there's too many. Like I don't have enough pins to address each segment individually. So you can
Right.
turn that whole Wi-Fi segment on or that whole Wi-Fi segment off, but you couldn't necessarily like show the signal strength going up or down.
Okay.
But essentially, once you have those constraints, you kind of draw up a. Let me see if I can pull this up. Yeah, here we go. So I drew up a data sheet that I sent to my LCD fabricator, and it was kind of like, here's my segments, and I drew a dotted line around the ones that are kind of joined up and only addressable as a whole thing. I
Okay.
gave them my dimensions, which are
So
kind of
this is
nominal.
just to be clear. This is your drawing that you sent to them.
This is my drawing. It's got the oddly specific
Oh, nice. Yeah.
watermark at the bottom. And I came up with a segment map that I thought made kind of logical sense because
Okay.
one of the things we're going to talk about in a second is how you actually route these things. And it's got to be a lot more tied to the physicality of the object than a circuit board. A circuit board, you can go even on 2 layers. You can jump things around from something on the right side of the board can connect something on the left side of your board really easily.
Yeah.
With an LCD like this, you can't really do that. Everything has to kind of route on 1 layer. So anyway, the point is when they came back with their data sheet, they drew routing. So
Okay.
here you
There
can
you
see
go.
my 4 common pins. So let's just follow this pin 0 right here, pin 1. So it kind of goes all the way around and it hits my colon. It hits these 2 segments here, these 2 segments here. I guess it also hits like these kind of two, like
Okay.
it hits the lower left two segments of each one.
Yep.
And then my segment pins here, you can see where, like, let's take pin 16 here. It connects to the bell, the Wi-Fi indicator, the moon, sleep mode, and the data indicator. Right. So by addressing common 0 and segment 16, you would light up the bell. By addressing common 1 and segment 16, you would light up the moon. So it's kind of like you have to like route these things where they so they can address each individual segment.
Nice.
So yeah, that's kind of the gist of how I designed it. I designed the artwork, made sure that it actually would make sense, like logically, in terms of only having 48 addressable segments, and then I sent it to my manufacturing partner, who figured out how to fabricate the thing.
So I think with your drawing, you had restrictions or constraints on which pins were driving which segments and which commons. So you had this knowledge already, and you knew what you were doing effectively. So
Yes,
is that
I will
something they
say
came back and they said, actually, we can't make that work? Can we change this over here, for example? Is that something that they
no,
had
but
feedback
that
with,
is,
or?
in this case it wasn't, but that's only because I'd kind of done this once before and I kind of knew some
Right.
limitations. Um,
Okay.
Generally speaking, you might not send the whole segment map like this. You might just say, my constraints are I really want my indicators on pins 5 and 16. Like that would
Right.
be a reasonable constraint, and they could probably work with that. If you had really specific routings inside that didn't like weren't, again, like logically routable on that kind of single layer trace kind of thing, they might come back with feedback saying we can't do that. But in this case, I was able to get kind of what I wanted.
Okay.
And again, the reason that I wanted this is I wanted the display routing to be logical. So let's take a look at pins 14 and 15 here, or sorry, 12 through 15.
Hmm.
So 12, segment 12 common 1 is segment 2B. That's the second B segment, right? Segment 14 common 1 is 1B. So you kind of see like
Hmm.
there's a BA, 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 BA thing going on here.
Got you.
So
Yeah.
I can use the same kind of single byte to address all 8 segments of an individual digit, because they each have a consistent like CF, CF, CF,
I see. Okay.
5G decimal point, 4G decimal point. The one interesting one, when they actually get some back and forth about this, but they wanted to put the negative symbol on pin 16, and I was like, no, the negative symbol feels like it's tied to the digits, not to the indicators. So I'd rather have the data segment on pin 16. And so the only difference is when you're writing the negative symbol, you have to like have a special case to handle. Normally that would be like the decimal point before the first digit, but instead
Yep.
it's the negative sign in front of the first digit, which, that's handleable in code. It's just like one
Yeah. Yeah.
special
That makes
case.
sense.
And a negative
Okay.
symbol is more useful to me than an extra decimal point.
So in terms of
Yeah.
driving this, then you've got an IC that deals with all of the signaling to the LCD itself. I believe that's some kind of AC type waveform. Does it have effectively a map like
Yeah.
this that you then populate with your data, and it then just deals with clocking it out to the LCD?
Yes. So I'm using the U9796 LCD segment LCD driver. Really great little chip. It's quite inexpensive. It seems to be consistently in stock, which is huge these days.
Hmm.
But effectively, it's just an I squared C chip. You talk to it over the standard I squared C bus peripheral, whatever you're used to, and it has its own display RAM. So essentially, you just write a single byte to your display RAM, and it translates that into the waveform it's going to put out on the segments.
Yeah.
So if
Nice.
you write 1 byte, it's going to control segments 0 and 1 and commons 0 through 4. So like it'll figure out
Gotcha.
how to like output a waveform that turns on the segments that you want to address right there.
Okay.
And it's actually really quite nice. You can do a partial write. So if you want to just write 1 byte, you can write 1 byte. If you want to write 3 bytes, you can write 3 bytes. You can even
Hmm.
write it an offset. So if you, let's say you had one of those like classic like ticking countdown clocks where you got your tenths of a second counting down, you could just send out 1 byte at offset 5 and say like I want to just like only update that 1 byte.
Nice.
And
Okay.
yeah, so it's a really great little chip. I highly recommend it. And I also highly recommend the LCD Featherwing if you want one. They're available
Of
for like
course.
Tindy and Adafruit.
Yeah. So, sorry, just to come back to the design. So actually looking at this data sheet, that's got the segment map as you presented it in your document to your manufacturer. So when you were drawing out your LCD, you already had in mind that you were planning on using this chip, were you?
Yes. Well, I was having in mind that I was going to plan to use this chip or the SAM-L22, which I eventually
Okay.
may do a feather with LCD that involves the SAM-L22. But in both cases, I think I see where you're going with this, the segments and the mapping. In both cases, I thought it was really important to have my segments, my indicator segments, the sort of Bell, Wi-Fi, Moon, and this guy data on and battery on the same line, in addition to the colon, because first of all, with the BU9796, if I want to write all my indicators at once, I can do it with one byte. Hopefully, we'll talk about how I got that done later. But number two, on the SAM-L22, the first two segment lines, segment 0 and segment 1, have the ability to autonomously blink. So I could put the processor completely to sleep and have it flash the battery symbol without consuming any CPU power, because it can autonomously blink that one symbol. So that's another reason that I wanted to make sure all my indicators were on the same lines. There's some other cool features in the SAM-L22, which probably out of scope for this talk, but yeah, so you really have to think. The gist of it, though, is you really got to think really thoughtfully about which segments you assign to which things, because sometimes your driver has special features like that you really want to make use of. Yeah.
So in this case, obviously you've got partial mapping, or sorry, partial updates of the display. Your segment map is like this, and you mentioned on Twitter before that you've got something secret going on here, some secret sauce to make it work nicely. Can you just outline that quickly for us?
Yeah. So if you kind of naively mapped like each individual thing, like 1 to 1, 2 to 2, you would end up with something that would work for sure. But you'd find yourself, if you wanted to update, let's say you wanted to update the colon as well as the sleep mode icon at once, you would have to write either two separate writes, one at offset 0 and one at offset 5, or you'd have to write the entire display at once. So my thought process was, I would love for the indicators to all be connected to one single byte logically on the bus. And so that's where I ended up in my KiCad doing this really, it looks weird if you don't know what I'm thinking, but if you like start from the left, it's like segment 1, 2, 3, 4, 5, all the way through to segment 10, segment 11, and then segment 0. Segment 0 is like not in where you would expect it to be.
Repositioned to the end. Yeah.
Right. But the reason for that is with sending a single byte over the I2C bus, I can update both segment 0 and segment 1 lines, which is my, as we saw earlier, my AM/PM battery colon and my Bell Wi-Fi data and sleep mode. So essentially, I get to update all my indicators with just one byte over the I2C bus, which actually has a significant power impact. Well, significance relative here, but it's a pretty useful power impact we can measure.
Yeah.
I can actually demo this. This is actually kind of a fun
that'd be
one.
Fantastic. Yes, please.
Yeah.
Just while you're getting that ready, it sounds like David's grabbed one of your Featherwings, which is awesome.
Awesome.
And he's also suggesting that maybe we could make a modern or a reimagined Game & Watch potentially. We're working with LCDs.
That's really fascinating. One aspect of that, though, is you got to hit a minimum order quantity for a lot of these things.
So
I had to order.
This is going to be a question that I was planning on asking. Please go for it. Tell us more.
Yeah. So you had to hit a minimum order quantity on some of these things. And in my case, I was lucky. I found a manufacturer that was willing to work with me on MOQ of 1000, which is like, it's still, I got a crate of LCDs in my corner. But it definitely wouldn't be something you could do for like a, small run, like 500 or 250 kind of situation.
Yeah.
Just for fun. But then again, I mean, just for fun, I don't know. Like if you really want to make 1,000 of something, it's within reach. Other manufacturers.
You've got this minimum order quantity of 1,000, which you found was, quite a low figure, and you were lucky to find them. But what does that mean in terms of financial cost? Is there kind of NRE cost up front, and then you've got your 1,000 parts, or how does that split out?
There's definitely an NRE cost up front. Without going into too much detail about pricing.
Yeah, sure.
And there's also tariffs to deal with. They can be quite affordable. Like at an MOQ of 10,000, these things cost less than $1 a piece. At an MOQ of 1,000, it was a bit higher, and I got hit by the 25% tariffs on coming into the United States. So and there's also the shipping, which is a pretty big crate. So it ended up being affordable, and the gadget does make sense at the pricing that I have it at. But it does require a bit of a commitment. So I'll just put it that way. Yeah. I mean,
and there's no. Sorry, carry on.
No, I'm saying I'm not taking out a loan for this. It's something that's within the realm of possibility for for someone who really wants to make a product. But it's also not something that I would just do on a lark for sure.
Absolutely, yeah.
Okay, so what do we got here? So I have here my start this here. This is my LCD Featherwing, and it's kind of naively updating the entire screen all at once. So that flashing colon you see in the middle, that is sending a full update of everything on the display. So like,
so that's a full frame buffer's worth over the I2C, and
full frame buffer over the I2C. And for what it's worth, it is going to sleep in between. It is going into standby mode. So it's not like we're like just running like full time on a loop. But the only difference here is like we're updating like 5 digits over the bus, or 6 digits over the bus every time we push an update. Sure. So that's demo number 1. And we're averaging what you see there about like 610, 620 microamps over the course of 10 seconds here.
Okay. Do you mind if I ask you just quickly pause that before you go forwards, and then zoom in on one of the spikes and just see sort of the charge involved? The coulombs.
Yeah.
Just because I'm intrigued.
And in fact, we can even shift and drag here. But yeah. Let me go like even kind of closer. Oops. There we go. And actually, this is useful because we can see the time. So the time spent updating over the I2C bus is about, what, 34 microseconds?
Can't quite read it from here, but take your word for it.
It's right. It's this number right here, 33.68 milliseconds.
Yeah.
So
okay.
So that's our,
and that's about 275 microcoulombs. Cool. Okay.
Yeah, just for our update. And so now we're going to plug ourselves in. We're going to, as I do this, I'm going to say, don't you just love the UF2 bootloader? I've got like a, oops, I've got my code all like saved as just a series of demos, and I can just drag on the just the colon demo over here.
Oh, very good. Well done.
And so now let's restart our demo at 10 seconds. And so now we're going to start to see our average. And whereas before we were looking at 620, 630, now we're looking at about 530 microamperes. So we've saved about 100 microamperes just by only sending 1 byte over the bus, which I think that's a pretty good win, you know?
Very cool.
And so now let's pause it, and we can zoom back in at our 100 microsecond level, and we can measure out that we are now spending 27.5 milliseconds updating over the I2C bus. So we saved some time, but more importantly, because I2C bus is active low, right? So as long as the lines are pulled high, you're not drawing any current. But as soon as you try to bring either the clock or data line low, you're pulling current through those 10K resistors, right? So, right? As soon as you have a zero, absolutely. As soon as you have a 0 on the bus, you're consuming current. So in addition to the less time spent updating and the less time spent awake, we've also got less current consumption by actually, like, we don't often think about like the current consumption of our signal lines, but that's a fact, you know?
Yeah, definitely. And looking at the charge as well, that's almost a 20% saving in terms of the energy you're spending updating the display, which is fantastic. Yeah.
So that was the little trick over here that allowed me to, so by rerouting this one little signal line, I've opened the door to saving a ton of like, not a ton, but like saving a measurable amount of power consumption. And I've also simplified my code because I can go over here to my driver code. And I'm actually quite proud of this little line here in the, it's in the LCD wing. So whenever we do the toggle colon, this is the update byte 0 method. But essentially, it's a show partial of 1. So it's just sending 1 byte over the I2C bus. And in our light driver here, like there's a display partial that can figure out like, okay, if you're setting byte 0, just like send this. Otherwise, have a position, you can set what position. Otherwise, you're just literally writing 1 byte at offset 0 and you're done. So it ends up making it really simple to just call this update byte 0 to update all the indicators at once with a single byte on the I2C bus.
That's really cool. I like that. Good job.
Thank you. So that's if there are any other questions about the custom LCD on this stuff, I'm just really stoked to share that because it was a
that's brilliant.
lot of thought went into that one routing.
I think so. Your design, as you said earlier, you drew that, you documented it and sent it off, and at that point you already had in mind, you thought ahead, basically, probably going to use a control chip like this. And I know that with the 5 and 16, I can sort of push them together and do the partial updates and whatever else as well. That's really cool. I like that. Very good. So I think that kind of covers the Featherwing. I'm not sure if anyone watching's got questions, but I can't think of anything to ask right now. But I like it a lot. Well done.
Thanks.
So if we move on to the sensor watch, if you're happy to talk a bit about that, this is something I've been following your progress on via Twitter, and it's fascinating to watch. Every now and then you go, yes, I got another few whatever's eked out of the power budget.
Yeah, totally. That was a fun thing to chase down, because actually, let me just pull up the Sensor Watch crowd supply page, because I feel like that would be a place to just show what the board looks like.
Yeah, please do. Yeah.
Actually, just crowd supply, oddly specific, Sensor Watch, sweet. So one thing that I kind of like to point out about the Sensor Watch is, I did this one. It was like a tour of the circuit board, but like one really interesting thing to look at on the Sensor Watch board itself is, I'll just use the main page. There's not that much on this board, like if you look at it, like what do we got? We've got some passives, obviously. We got an LED and this like connector, but in terms of like active silicon, we have a power diode and a voltage regulator, which honestly aren't involved at all once it's on your wrist. Those are kind of just not there anymore. Like there's nothing to regulate it. Therefore, when you plug into USB. So the purpose of that is when you're plugged into USB, you can't have a battery attached to the back. So this 3.3 volt regulator just is what's powering the SAM-L22 when there's no battery attached to the back.
Understood.
But once you clip it into its enclosure, it's just whatever the battery voltage is going directly to the VCC lines of the SAM-L22. So those are kind of moot. And the only real piece of silicon that's running on my wrist right now is this SAM-L22. So when I think about what can I eke out of the power budget, I'm not searching all around the board for things. That's pretty much, if there's power to be saved and it's not redesigning the board, it's going to be by by messing around with some code that's running on this microcontroller.
Very good.
Does that make sense?
Yeah.
So
fantastic.
Yeah, some of that microampere hunting was just there's some really subtle, and I can pull up the data sheet here. There's just there's a lot of these microcontrollers are very full featured devices. There's a lot of things you can do with them and a lot of configurability to them. So if I'm just gonna go to my LCD, let's look at the registers here. There's Control A, Control B, Control C, and Control D. All of these are different settings you can set, different options you can turn on or off. In addition to that, you have other options that aren't even on this page about how do you want to clock the LCD controller, and that applies to everything else in here. Let's see, yeah, I see. External interrupt controller was one really big one, where it's how do you? I'll just very quickly go through how I found some extra power savings in the external interrupt controller.
Okay.
I'm looking for a block diagram, but essentially you have to clock any peripheral, right? You have to give it a clock to do its thing. So you can feed, if you have let's say that you're doing something really latency is really important to you, and if you have something happens, you want to interrupt very quickly, you could feed it with a very high speed 1 megahertz kind of clock, right? And then it would detect any kind of signal change at that frequency and very quickly give you an interrupt. With the Sensor Watch, I'm only using the external interrupt controller to detect button presses, so I don't need that. So I'm clocking
I think
it
that
with
diagram at the bottom of the screen right now is super relevant to what you're saying. Yeah,
it's totally relevant. I was trying to find the block diagram, but this will work.
Yeah.
So essentially I was well, I'll just clock it using the same clock that I'm using for the real-time clock, which is a 32 kilohertz crystal, which basically the SAM-D and SAM-L series are really great because you can just take any clock source and kind of route it around to any clock, anything that needs a clock. So it's my external interrupt, my 32 kilohertz crystal is on global clock 3. I route global clock 3 to the input for my external interrupt controller, and now I've got a 32 kilohertz clock. Perfect. And I was doing that for a year. And then I was kind of turning on and off different systems. And I'm wait, my external interrupt controller is when I turn it on, it's consuming way more power than I was expecting it to consume. Like there's a document that has like expected like power consumption for SAMD
Yeah.
peripherals, and it's like, it's too high. What's up with that? And eventually I figured out that there is a special thing where rather than like using all this like clock routing, you can take the ultra low power but very inaccurate resistor capacitor oscillator that they have inside here and just pass that directly to the external interrupt controller, which isn't as precise as you would want for like a timekeeping purpose. But all you need to do is just see if the logic level is changed on the buttons. That is more than adequate for our purposes.
Not after precision. Yeah, exactly.
Yeah. So I ended up changing the, is it in here? Anyway, yeah, here we go. Control A, clock selection. So the IC can be clocked by the global clock or by the ultra low power clock when power consumption is the priority. This one little half of a line here saved me like a significant amount of power. Like we're talking on the like over a dozen microamperes. Like it's like, it took me from maybe it'll last a year to it'll definitely last a year and probably more. So cool. Yeah, it's so really like,
sorry, if I'm following correctly, you're using the 32 kilohertz external crystal for timekeeping. And so that's always running and up and running, doing its thing. But now you've changed the EIC from that 32 kilohertz clock to another low power 32 kilohertz clock, and you've reduced your power consumption.
Yes.
So that puzzles me because I'm curious as to what's going on there. You know, still running at 32-ish kilohertz. You've still got your big hungry clock running.
My thinking is this. My thinking is because like most of the peripherals on the SAMD, like you use this like clock routing kind of situation where you like just like take this clock input and route it to the ADC, and then the ADC is clocked at this rate or whatever. The only two that are different are the segment LCD controller. Well, I guess three. The segment LCD controller, the real-time clock, and the external interrupt controller all have this special case where you can bypass all that clock routing. And so my guess is that because those are things that you would use in an ultra low power design, Atmel or Microchip has just like made a special case for them where you can just like clock the low power clock directly in and not like deal with that overhead of like lighting up extra silicon with their clock routing, you know, logic.
Very cool. Amazing.
That's my theory
saved
anyway,
so much, but that sounds reasonable to me. Yeah.
It was really surprising, and it's like a really subtle difference here because yeah, you're right. It's the same clock rate, but there's clearly something going on inside where it's you can just like this, like if anyone's watching is familiar with the SAMD series, like you normally would not do your clock selection in the control register for your peripheral. You would normally do it outside, like the global clock kind of stuff. So this is different. This is definitely like a special case.
That
was a big one. That was like probably the biggest power savings I found while I was doing this microampere hunting.
well done for finding it.
But like that was the thing, like right, like. And if anyone's watching and like wondering how they like would go about doing this in their designs, I literally just went in and was like, okay, every time I enable something for my device, just comment them all out and enable them one by one. And then you start to figure out like what's consuming more power than I expect, or what's making that big jump. Yeah. So that was like,
I have to admit, I've gone into data sheets before, and you just type in and search for like power, and you just click through every single instance of power, and you're like, oh, this one could be good.
Totally. Yeah.
Anyway, so yeah, as you said, you've got this tiny PCB inside an existing watch body, which has got basically nothing on it apart from a SAM-L22. What else are you doing with that chip? Because surely it's more to it than that.
Yeah, I mean, this is where like I was saying, like these are really full-featured chips, but this is where like these microcontrollers, they're really powerful, not just in terms of like, they have more compute power than a lot of computers did, several decades ago.
No comment. Yeah.
But also, totally. But I mean, also like you look at those old like mainframes, and it's like it has all these options for attaching peripherals, and it's like now the peripherals just live on the chip alongside you. So like you don't let's say that you're building a clock, and you want to have a real-time clock, like to show like wall clock time, calendar time. You might be tempted to go out and like buy yourself a PCF 8547, is that the one, or DS3231? You might be tempted to go and buy a piece of a chip that you would throw onto your board, and that might actually be great. Like if you have like really like deep like accuracy needs, yeah, you can just get that DS3231 temperature compensated RTC, and it will talk over the nice word C bus, and it'll give you your real-time clock. But RTC. we have a real-time clock on this chip. Like, and it's,
Ta-da!
you know,
There you go.
actually pretty good. Like, it's not going to be very good if you use the low accuracy RC oscillator that's on board. But if you put an external crystal onto it, that crystal can be quite accurate. So you can actually get a really decent RTC without adding any more silicon to your board, just like adding a little, like, very inexpensive, quartz crystal on the thing. And then this is where it gets even more fun. Actually, maybe search for it. Let's say that you really do want that temperature compensated aspect of it, right?
Mhm.
Well, it turns out there's a frequency correction register on the RTC on the board.
There
So
you
if
go.
you have a temperature sensor and you want to, like, compensate for that, measure against the known clock, figure out what temperature, like, affects your crystal a certain way, look that up, plug it into the frequency correction, and you could actually, with just like a thermistor and a crystal, implement a reasonably temperature compensated oscillator directly on your board with your existing microcontroller, instead of having to go out and buy like a TXCO, and that DSD3231 would not fit inside the sensor watch. It's bigger than the microcontroller.
Fair enough.
Yeah.
So in terms of the sensor watch, the watch being the operative word here, have you done things like tuning the crystal and dealing with this frequency correction and things? Have you actually sort of approached that, or have you just kind of
I have
found that it
not.
works and it keeps track
It keeps
time
track
pretty well?
quite well. Like,
Yeah.
it keeps track as well as the Casio, which is like within a couple of seconds a month.
Okay.
One of the challenges is, like, temperature actually is a huge factor.
Mhm.
I mean, I haven't measured this particularly, but it's known that, like, the temperature, like, if at a colder temperature, the crystal oscillates at a slightly different frequency than at a higher temperature. Like, it's like there's some variation there.
Yeah.
But in my experience so far, it's keeping time to within a couple of seconds a month, which is good enough for now. There's two schools of thought in the Sensor Watch discussion forum on this. My school of thought is, let's get a GPS regulated, like, highly accurate clock and a frequency counter, and like measure the exact amount and like make a lookup table while I put the watch in the freezer and like put it in the oven.
Okay.
Someone else pointed out, if you just like measure how far off it is from a known good clock at the end of the month, we can figure out what frequency correction you need to apply for that. That might work, honestly. I
And I
don't
guess
know.
because it's on your wrist, it's probably at a fairly constant temperature, body temperature potentially,
Right, but then you take it
which
off at
means that.
night.
Say again.
But then you take it off when you go to sleep.
Okay.
So
I don't wear a watch,
yeah,
so I'm not a good one to
yeah,
comment on this one.
yeah. No, I mean, it's on my radar screen, and I know it's something that's possible because we shipped
Yeah.
it with that little temperature sensor board. So it's definitely like within the realm of possibility. I just
Neat.
have not had a chance to actually do that fine tuning, but
Okay.
I know that it's there.
Yeah, nice. So you mentioned just now the sensor board, and that I think is in the image of the board on the crowd supply page. You've got a little ZIF socket. Is
Yeah,
that where the sensor board goes? And can you talk to us a bit more about what that can do and what interfaces are available, etc.?
totally. Yeah. Let me actually pull up the Sensor Watch documentation page. Oh, you know what? It's linked at the bottom of this page because crowd supply is helpful like that. Sensor Watch. Yeah. So these little sensor boards, they look a bit like this. You can see that, right?
Yep.
Cool. Yeah, they look a bit like this. This little, like, kind of inverted L shape. It's got 9 pins, power and ground plus power and ground, I squared C bus dedicated, and then 5 GPIO pins, which can do quite a lot of stuff. So the temperature sensor that I shipped out, it's just a very simple thermistor voltage divider. It uses one pin as a active low enable and another pin to sample the like analog level of the voltage in the middle of the voltage divider, and we can turn
Okay.
that into a very accurate like reading of the ambient temperature.
And so when
Like
you
this
say
one,
that's an active low enable, is that basically the part is strapped between VCC and a GPIO pin, which you can then pull down effectively? Is that basically what's going on? Yeah,
that's exactly
nice.
what's going on, because it ends up being like it's a 10K thermistor and a 10K resistor, so you end up
Yeah.
consuming power through a 20K,
Yeah.
whatever load, I guess. So I don't want to do that all year long. I just want to do that very quickly when we
Yeah.
enable the temperature sensor, take a reading, turn it back off.
Sure.
I guess
Exactly.
this is also a kind of a low power strategy. I've just used it so often these days that I don't think about it. Yeah, like don't power your sensors when you don't need them.
Of course.
Um, But yeah, so this was an earlier one that I used the design, but this was before I realized that it's pretty watertight and humidity is not useful. But I had a temperature
Okay.
humidity sensor in here, and this one was an I2C sensor. So here it's power ground and then powered from a GAO pin because it's solo power. You can get away with that, and then I2C clock and data lines, and so you could just talk to this little chip over the I2C bus. I've done another one with accelerometer and a SPI flash chip, which is actually quite cool. You can like log a lot of like I was logging like motion data for things like running, things like being on an elliptical,
Yeah.
and it's cool. You just write it to an SPI flash chip, and then you can dump it out over USB serial or whatever. And I was able to like train a machine learning model with data that I'd collected from a board that fits inside this Casio wristwatch. It's
Amazing.
pretty
Well
cool.
done.
Yeah.
Very cool.
And
So
it's also one of the okay, good.
carry on.
And it's also one of the things about yes, like the SAM-L22 is like really powerful, and I can get away with like only having it on the board. But also the things that they're doing with like MEMS sensors these days is pretty incredible. Like we have a old school like analog devices accelerometer like breakout from like years ago sitting at well, I used to when I had my workshop in New York, we had it sitting there on the bench, and it
Right.
consumes on the order of like several milliamperes of power, and it just gives you 3 analog outputs. And
Yep.
now we've got accelerometers that are much smaller, consume on the order of 1 microampere of power, and give you like interrupts and like FIFO buffers and things. It's just
Yeah.
incredible. Like, so yeah, you can get away with like the area we're dealing with right here is just under like 7 millimeters by 7 millimeters. So it's a
Okay.
tiny amount of space, but it's enough, like
Yeah.
shockingly.
Amazing.
Yeah.
Very cool. So the just for clarity, the dotted line there, is that kind of a keep out zone that you're not able to put parts in because of various other
Yeah.
bits inside the watch?
So if you look at the front of the board here, that area is where the microcontroller sits.
Oh, I see.
So
Okay.
you're really only meant to put parts in this area, which contains the programming pins. And I always put like for anything with parts facing down, I recommend putting a little piece of Kapton tape
Sure.
because you don't want to accidentally make electrical contact. But yeah, so like that area is the dotted line area is the keep out, and then this area is where you basically uh, if on top of that microcontroller is like your little flex PCB, and then the LCD is like right there, so
Got you.
you don't have a
Okay.
lot of room on that side.
Yeah.
Um,
Fair enough.
yeah.
So looking at the board. Oh, carry on.
I was going to joke, like you could probably get away with putting a couple passives like right here under this dotted line
Right.
here, but I've never actually tried that. Sorry.
Okay.
Good.
Fair enough. I was just going to ask, in terms of looking at the board, you've got, I think, what might be an LED in the corner as well for presumably backlight or similar.
Yeah, so this is a dual color red green LED.
Okay.
And that's just again driven off of GPIO pins.
Right.
So you can, and oh yeah, that's actually a good segue into the timer counter stuff. But you can light it up red, you can light it up green, you can also do PWM, so you can light it up to any shade of like orange or amber,
Okay.
yellow kind of stuff. There's a really nice lime green it can do.
Oh, very nice. Yeah.
Yeah. So but
And
that's
presumably that can give you like feedback on something. It's not just a preference of what color you'd like. It's a matter of
absolutely.
this alarm is going off rather than that alarm or whatever it might be.
I long had the idea of if we get the machine learning stuff working, like it'll detect if you're washing your hands and light up red when you're not done yet and green when you've washed for long enough. Yeah.
Very good.
Yeah, like
Cool.
that was the really part of the thought process. Because like a user interface is a huge thing when you don't have that much like to work with. Like
Yeah.
it's a very simple segmented display. You can only get 6 like letters and numbers on the bottom row and like 2 and 2 on the top row. So it's very limited. And then like with the light, it's like so you got like 2 colors of light you can blend. You've got like very simple like segment LCD, and then you've got the buzzer which you can beep. But like that's it. Like it's not a lot to work with, but you can do a lot of cool stuff with what we or I guess I've put on here. Yeah, it's I don't know. I think it's like a really great canvas to kind of project things onto because it is simple,
Yeah. Very good. So sorry, just quickly before we move on, you've got the LCD and you've got the buzzer as well. Are either of those original parts, or is that something that you've produced? Presumably the LCD is something you've designed and remade or made
No,
in your own.
the LCD is the original Casio F91W LCD.
Okay.
Yeah,
I had not expected you
it's
to say
actually
that.
yeah, no, it's interesting. I actually reached out to an LCD fabricator with some like specifications based on the FNMW's LCD, and they were like, "We don't work with glass that thin. I don't think you're going to have a lot of success."
Oh wow, okay.
Yeah, which makes sense. I mean, Casio makes on the order of like several million of these a year, so they can do that NRE cost, and it's going to be a more complicated kind of design. But
Yeah.
once it's nailed down, they're just making so many of these that they can deal with this like kind of really thin glass and really fine pitch. Whereas for someone like me, I'm like, I'm not sure if you can see at the side here, but like the LCD on the Featherwing is like kind of chunky. It's a couple millimeters thick,
Yeah.
um, which like is thicker, I think, than anything inside the watch case of the sensor watch. So yeah,
Okay.
I reused the same F91W LCD. I got the segment mapping figured out, and yeah, we
And that
just
was
used
just
the
a matter
L22
of
to
trial and error to figure out the pin out and everything else.
totally. Yeah, one helpful hint though, if you ever like try to reverse engineer a Casio watch, I said that there's no vias on LCDs, but the way that their manufacturing process works, they need a little like dot of metal to connect the plane, the common pins to the back plane. So
Right.
if you look closely, there are. I wish I could. I'm not going to try to find this right now, but if you ever look at a disassembled F91W, there is three little dots at the top, like right out of view of the like bezel, and those three little dots are the common lines because that's how they break through to
Ah,
the back plane.
very interesting. Okay. Cool.
Oh,
Thanks for the tip.
yeah.
Your computer going to work, or are we going to
Let's
need to
hope so.
turn something off?
I'm forced quitting some stuff.
Sure, sure.
Cool. Yeah.
Cool. So original LCD. What about the buzzer? Was that original as well, or have you sort of? Yeah.
Buzzer is also
So it's
original,
just the PCB you've swapped out.
just the PCB. In fact, the buzzer, it's kind of cool.
Oh, one sec.
This
Yep.
back plate, the buzzer is actually glued onto it. So if you like
Okay.
take the watch apart, you'll see the metal back plate, and then you'll see a little like circle. And so the back plate is tied to the 3-volt terminal of the battery, and the buzzer is tied to a little like kind of flangey like pin that drives the buzzer when it's low. So yeah, that's not only is it an original part, but it's really kind of clever because if you imagine like trying to put a tiny piezo buzzer on the circuit board, it's not going to be very loud, and it's going to be inside this case. Whereas by like physically attaching it to the back of the metal, you end up getting like all the volume of it being like directly like attached to the part outside
Yeah.
it's vibrating. So yeah, it's a
Nice.
really clever design. I have like so much respect for the folks at Casio who designed this thing, what, like 30 years ago.
Yeah, that's neat. So one thing we were talking about before the stream was the fact that you've got. So we mentioned just now that all the peripherals are in this SAM-L22. You've got a timer count capture compare peripheral, and you've
Yeah.
used one to service two things. Can you talk to us about that? Oh, you've muted. Is that intentional? Welcome back.
No, like my head out.
Okay.
Sorry. You said that. What else?
So you've used the one single timer capture compare peripheral to service two functions features of your sensor watch. Can we talk about that a bit?
We can. Can I just really quickly? I need to restart my browser, but I will be right back.
Okay.
I apologize.
Yeah, sure.
Firefox seems to be running away with things here.
Oh dear.
Okay, I'll be right back.
Sure. Well, there you go. You've just got me for a minute. Apologies for the interruption, everybody.
Okay.
Welcome back.
Yeah, I for some reason Firefox was using 40 gigs of memory. I don't know what's going on there.
That's it's impressive. Yeah. Okay.
Yeah. Okay. Yeah. No, the timer counter and all that stuff.
Sounds like we've got
where
something
were
on
we
a
going back?
microphone. And it's not your headphones anymore. It might be built into your laptop, maybe. There's a lot of scratching on it. Sorry.
Yes.
Yeah. Don't worry too much.
Okay. Is that better?
Possibly. Let's go for it and see how it goes.
Yeah, no, so one of the cool things about the timer counter that we use, so there's 4 timer counter peripherals and one like called timer counter for control. It's kind of a timer counter plus. Um, and one of the things I wanted to, first of all, I got to use some of those internally. Like one of those is dedicated to like firing off a callback for USB stuff. And the other 2 I want to keep reserved for the sensor board, because I want the sensor board to be able to do, let's say you want to make a TV be gone and you want to PWM an IR LED to like turn off television sets. I want to leave the timer counter available. So kind of thought like, how can I like make most use of the peripherals I have? And the timer counter for control actually drives both the LEDs and the buzzer. There's a kind of a cool little hack that we do.
Okay.
Yeah, we can pull up code, I think, right?
Yeah, if you're happy to. Do you mind sharing your screen again when you're ready, just because you restarted the browser?
Of course, yeah. Screen 2.
Great, thank you.
Great. So we have the timer counter for control, the TCC, which
It's always the way with navigating code base live.
Totally, yeah. So yeah, so like there's a buzzer channel, a red channel, and a green channel, which you might think like, okay, well, how does this work? Like we are controlling light and sound at the same time. Well, interesting thing about a piezo buzzer, the way that it works is when you feed a square wave to it, it starts to like vibrate at that frequency, right? So frequency is what matters for a square wave. But like lower frequency will make a lower buzz, higher frequency makes a higher buzz. But ultimately, we just need to send a square wave like with 50% duty cycle for the buzzer to work, right? Then how does the LED work? How do you PWM an LED? Well, you've got to send it like a square wave with a certain duty cycle. So if it's going to be dim, you have it like high for less of the time and low for more of the time, or vice versa, right? But in the end, the crucial thing is the piezo buzzer like cares about the frequency, and the LEDs care about the duty cycle. So I can actually use the same like logic for both. I just need to figure out like, as long as my as long as the LEDs and the buzzer like aren't operating at the same time, or if they are, the frequency is within range for the buzzer and the duty cycle is in range for the LEDs, you can kind of get away with it. So I'm going to pull up here. Here I have my so there's the way you control the frequency is with the period buzzer. That's that PER register. So when I want to PWM the LEDs, I just say, okay, what's the current period of the buzzer of the TCC, because like that's what the buzzer is set at. And then I just tell my my CC buff here is that's sets the duty cycle of the yeah. So essentially, I just say like, take my period and multiply it by whatever I would need to make it overflow at the correct point for that duty cycle. So my LED is just like deferring to whatever frequency the buzzer has set, and then setting its duty cycle based on whatever is required for that. Whereas the buzzer just goes ahead and it writes its period, and then always has its overflow set to a 50% duty cycle square wave. So I'm able to drive both the LEDs and the buzzer using the same peripheral, which is great because now I still have all my other 4 timer counters free for whatever else I want to do.
So it looks like you've got an array of different notes here that you can pitches you can play out of your buzzer.
That is true. Yes, we got.
Wow! Okay, just a few.
We got the whole piano here.
Very good.
Yeah.
So presumably every time you change the pitch and then play that out, you need to also update very quickly the LED. Otherwise, you get sort of a flash of brightness or a flash of darkness.
Yeah,
and that's something you just handle automatically in your code base.
It's entirely possible you've just uncovered a very subtle bug that I've not encountered yet.
Oh no.
Yeah. No, I mean it is interesting though. I mean, you're right. I will need to handle that. But so far I seem to have gotten away with it.
Okay, nice. That's very cool either way. So I was expecting you to have chosen a pitch for the buzzer and then just turn that on and off, and then the
no, you gotta have chiptune apps, you know.
Absolutely, well done. Very cool.
I will say the buzzer definitely has a resonant frequency. Like it's designed
Yeah,
to be
yeah,
loudest at the frequency the Casio watch uses. So it's a little bit like lower at higher pitches and lower at lower pitches, but
yeah.
honestly, it's pretty workable. Like you can get a lot of different tones out of it. My
Nice.
classic
Okay.
demo was playing the Reigns of Castamere from Game of Thrones.
Oh, I missed that. I have to check it out. Let's see if I can dig it out of your Twitter. Very cool. So if we move on from the SenseWatch, that's been fascinating. Thanks so much for talking to us
Yeah,
about that.
totally.
You're also working on sort of a low power solar type design at the moment, and I'm not sure if that's really known about yet. Is that sort of a thing that
I
you haven't
haven't
spoken about?
I haven't spoken much about it. I kind of like tweeted some cryptic stuff just because it's been kind of a wild couple of weeks. I've been just really busy all
Sure,
over the
sure.
place.
Yeah.
But I'm helping a colleague who's an artist with an outdoor art installation where the requirement is we have some things that light up at night in the twilight, but then there's no external power available, so it's got to harvest solar power for it to work.
Mhm.
So right now I'm in the point where I'm using like Adafruit has a great solar charging breakout board, and I'm using that and some existing feathers. But I'm like really thinking a lot about how am I going to manage a power budget because I need it to be extremely low power during the day because it's going to chew up a lot of power at night when it's lighting up these LEDs. And
Mhm.
so I'm thinking about, how like what do I need to be doing to consume power during the day? And the answer is not much, right? Like I don't have any really tasks to do. My tasks really start once it starts to get dark in the evening. So what are my options? I could wake up every 60 seconds and like check the time, which could work and actually might end up being what I'm doing in the end. But my thinking for this, at first at least, was I want to use a peripheral on the SAMD series, which I feel like doesn't get a lot of love.
Mhm.
There's this thing called the analog comparator. And so this is, actually, I'll pull it up on the SAM datasheet.
Sure. Yeah.
So everyone's familiar with the ADC, I would imagine. Like it's, you set a pin to an input, you read the voltage level of that input, and you have a chance to see like, okay, like with we do with the temperature sensor, what is the voltage level on that? Translate that into a temperature reading. Cool.
Mhm.
Um, Analog comparator is interesting because what it essentially does, you have only 4 analog inputs on it, and their pinouts a little different on various boards. Some feather boards might not have all of them, but if you have them, you can compare an analog value to another analog value kind of asynchronously. So you don't actually have to be waking up and doing this comparison. The analog comparator just sits there and does it for you. Kind of like
Okay.
an op amp where you have like a threshold voltage that like causes the output to toggle.
Mhm.
Um, and so in this case, I'm able to. I'm going to show the demo in a second, but I am.
Mhm.
Let me pull up the video. I'm Mel
Brilliant.
Feather here, and I have this potentiometer standing in for my light sensor. So when the light
Yeah.
sensor has this like way to switch between above and below the threshold voltage.
Okay.
So this is kind of in the same realm of like trying to get the
Do you mind
most out
just
of
going
all your.
back and showing the little LCD more clearly? So I think we
Oh
might have
yeah,
missed
yeah,
that one.
yeah. So it's I'm turning the potentiometer, and I've got like below, above,
There you go.
below,
Okay, magic.
above. So like there's a
And so
threshold where I want to.
the comparator is taking care of watching that threshold and sending you an interrupt to deal with the change in value effectively.
Totally. And what's
Yeah.
more, it's not even like there's no active clock even going to the comparator. The comparator, to my understanding, is just kind of sitting there, and like it's only like toggling when the actual value changes.
Mhm.
Is my understanding. Um,
Okay.
but yeah, so like this is a really like interesting peripheral, I think, and it's one that I don't see people talk about a lot. But so you can have these like let's say analog input 0 and 1. So you could have like a constant voltage level on input 1 and like a voltage level that varies on the other one, and it could tell you when it flips across. Another cool thing that it has is this thing called a VDD scaler, which let me pull the scaler. This is what we do. um, uh, Basically, the VDD scaler it's not quite a DAC, but it lets you select a voltage level among 64 different levels. So you don't
Oh
actually have
wow.
to create a resistor divider outside to like feed into this analog input 1. You can just say I would like my VDD scaler to like have my threshold set to like 0.5 of my analog reference voltage, and that can be your negative input. So it's a really cool way to like get a
Okay.
lot of like this peripheral is like really cool at doing what it does, and it's not going to be useful for everyone's use case necessarily. But for my use case of detecting when a light level crosses a certain threshold, it seems kind of ideal, doesn't it?
Yeah. So I was going to ask, are you basing your activities in the evening on the clock wall time, or are you basing it on the light level? So because if it's on the light level, then actually you don't care if you run out of battery, so long as you have charged up by the time it's nighttime again, if that makes sense.
We had this exact discussion, me and my colleague who were doing things like, yeah, it almost doesn't matter if it dies as long as it charges back up, because who cares if it dies at 4 a.m, right?
Yeah.
Yeah, no one's out at 4 a.m. Yeah,
Whereas if
that's
you're trying to follow wall time, then obviously you need to maintain the clock, you need to have the power, you can't die, etc.
totally, yeah. So it's that honestly, like, it's one of the reasons that this like light sensor thing makes a lot of sense. As I imagine I will also have a clock. I'll use the real time clock peripheral, because if it turns out it's 4 a.m, we've still got some charge, I could probably turn off the lights and no one will notice. But it is very cool to like say I know that I have this like very reliable sense of like when is the sun going to set without having to maintain any internal state. So yeah, that's oh, and then this one other thing before we move on to the demo. I was going to say it's also got 2 analog comparators. You can even set these up as a window. So if you had a thing where you needed to know if like a level was too high or too low, you can gang them together and get an interrupt when you're within the window and outside the window. It's just a really interesting peripheral that I'm excited to play with.
Yeah, that's very neat. Cool. I think the band gap presumably is like a 1-ish volt supply that's used for the ADC and other things as well, I imagine. But
yeah, it's an internal voltage reference peripheral, manages that band gap voltage for you.
Yeah, neat, cool.
So, yeah, so I can actually do this demo thing if we want to give it a shot. Do we have time?
That'd be great. Yeah, go for it.
So first I'm going to, and this design is not like power optimized at this point, so we're just going to be looking at, relatively speaking, like how much more it takes. But first I'm going to drag on this first firmware that is sleep. So this is going to be our baseline.
Okay. And can you just describe quickly what it is this firmware is doing?
It is going to sleep and doing nothing else.
I see.
So yeah, basically this is the base case of what is the like baseline quiescent current draw of this board with nothing else going on.
Understood. Okay.
So let's start our measurements here. And that's when I say this isn't a very optimized design yet. A lot of that 155 microamps quiescent current is my voltage regulator. I did not select a very low quiescent voltage regulator for this project because, yeah, I didn't know what I was doing.
Prototyping, proof of concept type stages.
Totally, yeah. So this is where we are with just the microcontroller sleeping and the quiescent current of whatever else is on the board. So now I'm going to plug in my potentiometer, which it's a 10K potentiometer. So you're going to see we're now drawing current through this resistor divider. So obviously it's going to be drawing more. So our baseline here is going to be 617. Like that's how much, 615 or so, right? That's how much current we are using just in sleep. So now let's go back to our firmwares and plug ourselves in. I lost my plug. So now I'm going to drag on the, call this analog input. So this is kind of naively doing what you might do in Arduino, where you have just actually, I'll just pull up the code. We just have our loop function that triggers an ADC reading, waits for it to be ready, and then compares it and will print out whether it's above or below. So we've now got our, unplug the USB. So now you see where we're at about 850 microamps, but we do have our functionality where we want it to be. We can now trigger and see above or below. So
and is that just running around the loop, or is it having a small pause in there at all?
It's just running around the loop. So this is kind of the naive solution, the Arduino setup loop kind of solution. So now let's go back and drag on our analog comparator version, which as I do this, I will also pull up the code for it because it's useful to just see how it's set up. So our analog comparator version is, we have a lot of setup here, but effectively the value here, we're setting it to, there's values from 0 to 63. We're setting it to
Yep.
half our VCC. And then our AC handler just waits for the interrupt. And ignore that toggle, that actually doesn't matter anymore. We read whether the state is above or below, and we print it out, and then we go right back to sleep. So now let's see.
And so again, this is
current consumption looks
sleeping,
like.
or this is just running around the loop forever?
This is sleeping. So it's sleeping until it wakes from an interrupt, which in this case is the analog comparator interrupt. So let's go back to our thing. Wait, where am I? Video. Actually, maybe my sleep sketch was doing more than I thought, because now we're at 430 microamps.
Even better.
But the point is, you can see the interrupt here when we like get right below the threshold. It wakes up for a second, it does a thing, but otherwise we're just in like a really low current kind of situation here.
Brilliant.
Yeah.
That's quite a spike, actually, isn't it?
It is, but I'm not sure how much of a spike. I'm actually curious now. Let's do this and stop. Let's see here. What is a max here? 15 milliamps. I mean, I guess because it's in such a low power mode, it's like there's like a
turn on surge.
What do you call it? A surge current. Yeah. But yeah, so that's the gist of the.
No, that's very cool. So the idea here being that you follow the light level in place of that potentiometer, and as the level drops below threshold, you then wake up and do your evening stuff.
Mm-hmm. And then then the evening stuff will involve like lighting up a few LEDs, so it's going to be a high current kind of situation. But during the daytime, we basically just get to go to sleep until the light meter says it's time to wake up.
Yeah.
Which during that sleep mode, again, without too much low power optimization, we're at not that many 430 microamps. So yeah.
Nice. Very cool.
Yeah. We can get that down.
I think so, yeah. Good stuff.
So yeah, that's.
So is there anything else you'd like to talk about on this project, or should we move on to, I think, our last topic for today? Running a bit over time, but that's okay with us. You happy?
You don't mind?
Yeah, great. Yeah. Okay. So
yeah.
In that case, carry on. You go for it.
No, I was like, well, go for it.
Okay, so I think that the last topic then we've got for today is the open book, and just a bit of a talk around the design considerations you made and put into that.
Yeah. So this is like my long-standing sort of white whale of a project. I'm going to grab the other book really quick.
So I guess
I've been trying to design.
It's the what is this? This is effectively an open source, easy to make and assemble e-reader. Is that right?
That's the premise. So the idea is it's an ebook reader that you can build yourself from scratch. And I've been trying to, through various iterations since like early 2020, late 2019, trying to build this thing. First, it was a Featherwing. So it was like you plug a feather into it and then you have your peripherals on it. Then it became this version, which actually, it is feather compatible, but it has a microcontroller on it. So you build it, and then you could plug a feather in here that does like audio playback. You could plug a feather in here that does GPS or things to turn it into something besides a book. But this design reflects like where I was like years ago, not years ago, but like at the beginning of my journey, where it's like throw the kitchen sink at it to put everything you could possibly imagine onto this board. So this thing has got like microcontroller, but it's also got things like it's got a headphone jack, for Christ's sake. Like it's too much stuff, too complicated. And a lot of these like fine pitched parts, like this little microcontroller here, like that's 0.5 millimeter pitch. Like I can deal with that, but I don't think it's actually fair in hindsight to call it you can solder this together yourself unless you have some decent service mount experience. So the other thing about having the kitchen sink on this board is I looked at the BOM cost and thought, it's on the order of like $50, $60. You could do this. But then if you actually try to design for manufacturing, every placement adds cost. Every like placement adds like yield problems. Like this is like, if you can get away with less, you're probably going to be a lot happier. So I've been like kind of trying to optimize the design really aggressively. and grab this one actually. I've now reached the point where we're using the Raspberry Pi Pico board and the and AAA batteries, rechargeable AAA batteries, to try to like get rid of as much complexity as we can. So this board is now, I think, super simple and super workable. Like you've got a power switch, you've got a reset button. These stemma ports are optional; you don't have to do those, but I put them on for testing. The two MOSFETs. Actually, maybe just put it on the.
I was gonna say, do you want to put it on your screen?
Down cam.
Yeah, there you go.
Yeah. We've got two MOSFETs here to control power supply, passive to filter power. Castellated modules means that we can just like, instead of having to solder down all these finicky parts in this fine pitched connector, we just solder the joints right here and the mounting points right here and here. And your castellated module for the e-paper driver is just one piece. Same with the Raspberry Pi Pico. Instead of having to solder down a microcontroller and a USB port and all of these fine pitched parts, you just put down this one big castellated module, and that's the brains of the operation.
Yeah, brilliant.
Button, flash chip, a couple more passives, SD card slot. That's it. That's the extent of the parts required to build an open source ebook reader. So I'm really, really proud of like where I've gotten this design. It's not final yet. I do think eventually I'll want to have a LiPo charging on here, but by getting rid of the LiPo charging circuit, it got rid of another fine pitched part. It got rid of it's at least like 5 parts, including like passives and stuff, to support a LiPo charging circuit. Now I don't have to do that. You just put down this like really chunky, really friendly AliExpress battery holder, and then it's your responsibility to take the batteries out and charge them on the wall. So that's how I've been trying to like just simplify this design. So turn this guy on.
Great.
Thank you.
So are these running fairly similar type functional firmware, or is it, because obviously there's quite a different processor behind the two variants here?
Yes. So this version was still running the old firmware that I like wrote in Arduino. This I've been using Platform.io to come up with like a new firmware from scratch.
Okay.
And it's
actually
the one
you're holding right now is based on the Pi Pico, is it?
Oh yeah, this is also a Pi Pico version. You see the speakboard here. Yeah, this is the Pi Pico version, and it's running. I built this firmware in Platform.io using a GUI framework that I'm developing. I'm calling it Focus.
Nice.
And yeah, essentially, it's just I need to paginate the book, break it up into pages so that it can be seen. Essentially, you've got your like main text of your book right here. You got a little progress bar at the bottom that shows you where you are at in the book. And I mean, honestly, it's quite functional and usable. I reread The Great Gatsby recently, like on an open book with Pi Pico, and it worked. Like it gets out of your way. It lets you read. I'm feeling really stoked about it, and I'm hoping to have some kits to put together and send out very soon so people can start to build these themselves.
Yeah, I love it. So what's the plan? Is this open source already? Are you aiming for crowd supply again, that kind of thing? What's the longer term plan?
So for this one, I've chatted with the crowd supply folks before. I think that this version, the one with the and I should also say, I finally have my final PCBs. They just came in literally today. So
shiny.
Very shiny. If this works out well, PCBWay is actually interested in sponsoring like a run of like 50 boards for a kit or something like that. We'll see how it goes, but it would be very cool to send these out as a kit, like with all the parts. I have like the screens, I've got the battery holders, and just tell people like, if you want to build this yourself, this is like the developer preview edition. You can like build this, start hacking on the software, play with it. If I ever do a version for crowd supply, it would have the LiPo charging circuit, and it would have the LiPo battery, because I don't think that this it's kind of a chunky thing to have this like battery pack sticking out the back.
Sure. Okay.
My new enclosures have a little. Actually, let me just grab one of them. My new enclosures do have a little like thing where I imagine I'll be able to snap a battery like protector on the back, but it still feels like a little bit of a not fully baked for a crowd supply campaign. Whereas if I can I have these like really nice slim LiPo batteries that will make it effectively this thin on the entire device, which I think is a good thickness and size for an ebook reader.
Brilliant.
So yeah,
Very
this
cool.
this version, developer preview edition. Hopefully, folks seem to like it and the thing makes sense, I would love to do a crowd supply, because it wouldn't be that much bigger of a bomb. Like, we would obviously place down the individual passives instead of having this castellated module, because that's more
Right.
designed for manufacturing oriented.
Yeah.
But yeah, I have high hopes.
That's fantastic. Thank you for sharing that as well.
Yeah, thank you.
I have to admit, I love the just the wall of text on both sides of the board.
I mean, I think, Greg, someone pointed out on Twitter, like, they're going to charge you the same amount for silkscreen regardless of whether you use it or not. So why not use it?
And does the text describe the functionality, what components are where, why they're there, etc., or is it kind of a secret message to someone who?
Yeah, the old version actually did do that. The old version
Okay.
like explained how the power supply worked. It explained, but like this is the
I think
Babel
that's the one I was
Babel is like
thinking
the
of
name for my
before.
code name for the. Yeah, my code name was like Babel is like my Unicode display library that it supports like all the languages in the basic multilingual plane,
Okay.
and so you have to have 2 megabytes of data to like just kind of store all those glyphs. But it's like explained. Use 6 as a flash chip that has this that holds the bitmaps. So that was what I did before. For this new version, since it's aimed at like DIY assembly, it's actually just instructions on how to build it. So Soldering Suggestions has some very like basic things about like how you place things. Like, note that C3 is slightly smaller than C1 and C2. Be sure you place the small capacitor on this footprint that's smaller, and then you walk around the board and it tells you how to solder on the on-off switch, how to solder on the reset button.
I love that.
Yeah, so it's instructions this time as opposed to descriptions.
Yeah. And a hidden one under the Pico in the end as well.
Yeah.
Fantastic. Good stuff.
Yeah, I'm really stoked to put this together. I literally just got this like half an hour before this stream was about to go live. So I'm really stoked to put this together and see it working. I also like the white. The white, black and white feels really interesting.
It almost feels like it's a finished part already. Looking at the front there, it's almost feels like you're reading off the e-ink already.
I like that feeling, right? It's like, it explains itself.
Yeah, brilliant, nice. Thank you. So I think if you're happy to carry on a little bit longer, we've got one last topic we might like to talk about. I don't want to push you.
Which topic was that?
So this is about sort of test jigs, testing procedures, and getting other people to do it for you.
Yeah. We can try that. I don't have the test jigs on me. Is the one thing.
Okay. No worries. Are you happy to talk about that?
Yeah. Yeah. Totally. So yeah, like, I mean, this is kind of the whole thing about scaling up from making a few to making like a few hundred, right? Like, how do you like streamline your processes when you're just soldering a gadget together and then like playing with it? That's one thing. But now, like, I'm going to have to ship out over 1,000 sensor watch boards. So designing a test jig with like pogo pins and things is a huge, it's part of that process. Yeah.
Yeah. And how did that go? Is there any sort of learnings that you'd like to share, or you said you haven't got it with you, unfortunately, but the photo of the board, we saw the pads that the pins presumably touch down on, and etc.
Yeah, and one thing, the LCD Featherwing. So at the LCD wing, it's normally like designed to like solder in with like you. It comes to you as something where you solder in the pins of the LCD and you solder in the feather headers. So my test jig had to have a way to test those without actually soldering all those things together. Right. So in this case, like my pogo pins connected to the I2C lines, the reset button, power and ground, and then there was a row that connects to an LCD that's on the test jig. And when you press it down, my test procedure, you press the reset button on the wing, which obviously tests that there's continuity, and the reset button actually resets the device. And then it runs through like a little test animation of each of the segments on the wing, and that like will let me visually confirm that it's like all the connections are correct and like the I2C communication is working. So that's that. Man, I really wish I had the sensor one.
Is that kind of a thing where you're running through each segment, and being as the operator, you now need to know what the pattern looks like, or does it kind of guide you through this is what it should look like and reduce the step count, etc.?
In this case, it's the operator has to look at it. It is pretty obvious. Each indicator comes on once, and each segment like lights up like in a like 1, 2, 3, 4, 5, 6 kind of scrolling marquee.
Okay.
So it
right.
would be very obvious. Like I have one where so far I've only had one like failure, quote unquote, and it actually turned out I was just holding it wrong on the test jig. But it was very immediately obvious to me, like none of the indicators on the right lit up. This is a problem. And so I
Right.
retested and figured out that was the issue.
Okay.
But yeah, so it's one of those things where visually it's very obvious.
Yeah.
That's different from the sensor watch where obviously that jig I press down and it flashes firmware and it has a thing that like beeps and does all the whole thing. So yeah.
Mm-hmm. Okay. And then presumably for the open watch or sensor watch, sorry, you're planning on getting someone else to do this because of the volume involved? Is that
At this point, I'm going to be doing it all myself.
okay?
This is actually a broader conversation, but I think I priced it at a point where I would have to do this all myself for it to make sense.
Right.
I'm curious in the future whether I will want to raise the price of it to actually have someone be able to do that for me because,
Right.
and I need to talk to my manufacturing partner and also just like, yeah, I need to understand what that would look like because yeah, there is
Sure.
labor involved, and right now it's my labor, which I'm fine with using some of my time for this purpose, but
Yeah.
if we ever want to do another larger run of these, I would love to not have to do all of that myself.
Absolutely. Yeah.
And then there's the broader discussion about like how do you price your gadgets, right?
Yeah.
Because if it's like something that I can do myself and like I can handle the packing and the shipping, I can price it one way. But if I actually baked those labor costs in, maybe I would actually be pricing it higher. Maybe I should be is
Right.
a broader point. But yeah.
Yeah. Okay. Fair enough.
So yeah, right now all done here. In the future, like I would like right now I also outsource my PCBA. Like I have my manufacturing partner, Cyber City Circuits in Augusta, Georgia, does the assembly. They do also offer services of like testing and packing and kitting. So I need to figure out with them like what that would cost and like
Potentially a
yep,
thing for the future. Yeah.
yeah. Well, and the fact is like I've got colleagues like who are really into like the watchy kind of world, and it's like not watchy the product, but like the watch oriented kind of world.
Yeah.
And the fact is, if this went like big on the internet and people are like, you can buy this little gadget to turn your Casio F91W into a sunrise sunset complication, people not only would buy that, they would probably buy it for more than the $35 I'm selling it for,
Yeah. Okay.
So if it turns out that actually making like building the test costs into the device and then raising the price of that thing makes sense, it might actually make sense enough for a larger market as well. I just,
Yeah.
I don't know that it's a, have me on some time, show and tell, and we can talk about pricing gadgets. That would be an interesting conversation.
That'd be nice. Okay. Very good. Cool. All right. Well, I think that's probably good place to stop for today.
Sounds good to me. Yeah.
Anything else you want to say? Just last words kind of thing?
No, I mean, I guess the only thing I would say is like, I guess you kind of get this from like the way that I design things, like putting like instructions on the board, putting like, descriptions of what things do on the silk screen and open sourcing everything. I think a lot of my practice is not so much about like I make cool gadgets and more about I believe the people can make cool gadgets on their own. And I want the devices that I make to kind of teach that process because we live in this world where like tech companies kind of build the technologies that they want you to engage with and only in the ways they want you to engage with them.
Right.
And it's like, that means that your ebook reader like has a full Linux stack with networking and, monitors every click and sends it to Jeff Bezos to find out like how you're reading what you're reading. And if you didn't have that requirement, could you make something that's much cheaper and runs on a microcontroller that you can get for $4 and have more control over how you want to engage with it, Yeah. So I think that's the thing that I'm trying to like do with my practice. Like say, I want you to feel empowered to make things the way you want to make them and to take the designs that I've made as a starting point for the things that you want to make. So yeah.
Awesome. I think that's a great thing to be working towards. So well done. Thank you, etc.
Thanks.
Great. Well, thank you very much for coming on this week. It's been really interesting to talk to you. You've shown
us
it's
been a great time. I've really enjoyed chatting with you.
Been fascinating. So yeah, thank you very much. Next week we'll be talking with Sam Underwood about experimental musical instruments. But that's all from us today. Bye, everybody.
Thanks, y'all. Bye.